Okay, the enthalpy of formation of oxygen is 0. Other questions? The answer is plus 19.5 kilojoules per mole.
Did you say positive? Or
yes, positive.
okay.
All right, so let's move on to a concept called bond energy or bond enthalpy. This is very similar in concept to bond dissociation energy. So we define bond energy or bond enthalpy as the change in energy or change in the enthalpy when AB gas goes to A gas plus B gas. So if we are looking at the bond enthalpy for the CO bond in methanol, we're looking at the formation of CH3 gas plus OH gas. Can you write the corresponding equation for the bond enthalpy for the OH bond in methanol? Could you write the chemical equation for the bond enthalpy of the OH bond of methanol? So what's going to be on the left-hand side? What's going to be on the left-hand side? It's going to be CH3, OH gas going to CH3O gas plus H gas. This is the bond enthalpy for the OH bond in the methanol molecule. Okay?
Why is that not an OH?
Because you're breaking the OH bond here.
And then so the example is written here, that's for the CH3 OH bond.
It's for this bond here. That's the example over there. The example here is breaking the OH bond. Sure.
Also, do you not have to make it H2 on the side?
No, no. You're breaking it apart into the constituent pieces of that bond. Okay, let's look at this table here. It turns out that the CO bond, this CO bond, in this case is plus 380 kilojoules per mole. And what you find in this table is that if you look at the CO bond for hundreds of compounds that contain the CO bond and average over it, the value is about 360 kilojoules per mole. The CO bond is approximately the same strength going from one compound to another, and therefore you can average over a lot of compounds and talk about a quantity called the mean bond enthalpy. Mean means average. Mean bond enthalpies are useful because of what I just said. The bond, a particular bond has approximately the same strength over many different compounds. The CO bond in methanol is approximately the same as the CO bond in ethanol. Okay? The amount of energy required to break the CO bond here and the amount of energy required to break the CO bond here are approximately the same. That's why bond enthalpies are useful, and we can talk about mean bond enthalpies. Okay, I'm going to let you do this problem at your leisure. Actually, the speaker today, who is going to be talking about, has done some of this work, some work related to this reaction here. I hope many of you can come. I'm giving extra credit for the midterm for either coming to this talk today or for the reading that I gave you in that email message.
Can you get double extra credit?
No. Okay?
Which one is the
Does anybody know?
278. Yeah.
278? Yeah, it's down there on the second floor. All right. So what I want to now talk about is something called calorimetry. So far we've been talking about heat absorbed in a reaction, heat given out in a reaction. How do we know how much heat is given out? The answer to that is to use a technique called calorimetry. And this is what is called a coffee cup calorimeter. This is what you're going to use in the lab. Have you started this experiment already? No. This week?
Yeah.
Okay. Those of you who had lab on Thursday, what did you do? Did anybody have lab on Thursday?
Yeah, we did the halogens and
Oh, okay. All right. Okay. All right. So this is a coffee cup calorimeter. It's a constant pressure calorimeter. So in this case, the equation that we are interested in is delta H is equal to Q. If you measure the heat, you measure the enthalpy change because it's an isobaric process. You have a stirrer to ensure that the water is mixed very well. You have a thermometer to measure the temperature rise when a chemical reaction occurs. And you have a styrofoam container. Why the styrofoam? Keeps the heat in, and therefore it's a more accurate way of measuring the heat given out in a chemical reaction. All right? But before we talk about calorimetry, we have to define certain quantities. Here is the definition of heat capacity. Can you put this definition in words? So, capital C is the heat capacity. What is Q? Heat. Delta T is change in temperature. So how would you define heat capacity? Somebody raise their hand and give me an answer. Sinead?
the amount of energy it is to raise temperature to 1 degree.
The amount, very good Sinead, the amount of heat required to raise the temperature of an object by 1 degree centigrade. How would you define the heat capacity in terms of Kelvin? What is the heat required to raise the temperature of an object by 1 Kelvin? It's the same. Okay? A delta T of 1 degree centigrade is the same as 1 Kelvin. So, raising the temperature by 1 degree centigrade is the same as raising the temperature by 1 Kelvin. Okay, here's the definition of specific heat capacity. Simple C, capital C, what is M? Mass. So what is the definition of specific heat capacity? Yes, Anna. Exactly. The amount of heat required to raise the temperature of an object, 1 gram of an object, by 1 degree centigrade.
To raise the mass.
Raise the temperature of 1 gram of a substance by 1 degree centigrade. Okay, can you derive this equation here, please? Okay, so you can see that Q is equal to capital C times delta T, but capital C is M times C, therefore Q is equal to MC delta T. Very, very important equation. You will be given this equation, but I think you will use this equation in so many different courses, it may not be a bad idea to memorize it. Okay? So what this equation tells you is if you know the mass of the object, if you know the specific heat capacity, and if you know the change in the temperature, you can figure out how much heat is absorbed in making that temperature change. All right, let's look at a question here. Can you do this problem here? So here are specific heat capacities of different substances. And these are molar heat capacities. This is the heat capacity per gram. This is the heat capacity per mole. So can you do this question here, please?
Does it really produce so much heat?
Yes.
And the answer is the answer is
120,878.07.
okay, you got to be careful about
0.08, sorry.
you have to be careful about sig figs. Okay? The answer is 129 kilojoules.
129 or 129,000?
I said kilojoules. Yeah. Everybody get it? No? Okay, so Q is equal to 466 times 4.184 times 74.60. Oh, sorry, 74.60 minus 8.50. All right, let's look at the bomb calorimeter. The bomb calorimeter is isochoric, constant volume. Why is it constant volume? Because this container is a rigid iron container, stainless steel container. We'll fill this stainless steel container with oxygen to about 30 atmospheres. Put the substance that you're interested in a crucible. Put wires that almost touch each other next to the substance. Pass a current. Cause the substance to ignite, burn, produce carbon dioxide and water. The heat given out goes into heating up the water that surrounds the bomb calorimeter. We have a stirrer to ensure that the water temperature is uniform, and we measure the temperature rise with a thermometer. This is one of the most precise ways of measuring heat given out in a chemical reaction. In fact, a lot of the foods labeling about how much calories a particular food substance has is obtained using bomb calorimeters. Okay? And you will do one of these experiments in your first P-Chem course, not next year, but the year after. Okay, so here is the equation that we want to use here. The heat of the reaction, this is what we're trying to measure, plus, what is this? What is this quantity here?
Isn't that
That's the Q of the water. This is the heat absorbed by the water, plus, what is this? This is the heat, Lauren? The heat absorbed by the bomb calorimeter. The heat of the reaction plus the heat absorbed by the water plus the heat absorbed by the calorimeter is equal to 0. Yes?
So when you say the heat of the core,
I said the heat absorbed by the calorimeter.
Yeah. Is that just referring to the metal part that's?
Yeah, I mean that whole entire item here, this whole thing here. Okay, that's the heat capacity of the calorimeter. Okay, using this equation, can you try to do this problem here, please? Okay, because I showed you my son, I got to show you my daughter. She's 14, going on 25. So in this question here, we're going to assume that no heat was absorbed by the styrofoam cup calorimeter. Okay? And you're going to make that assumption in your lab also. So we're going to set this term here to 0. It's a big approximation. So what is Q reaction here? There's no real reaction here. So what really is Q reaction here?
Would it be the heat capacity of...
But I asked Q. Q cannot be the heat capacity. Q has to be a heat quantity. So what is Q reaction in this particular case?
Change the temperature of the iron.
It's the heat lost by the iron. Okay, the heat lost by the iron plus the heat gained by the water must equal 0. So the heat lost by the iron is going to be a negative quantity or a positive quantity? Negative quantity. And the heat gained by the water is going to be a positive quantity. What can you say about the final temperature? What can you say about the final temperature of the water and the final temperature of the piece of iron? I can't hear.
They're equal.
They're equal. The final temperature of the water and the final temperature of the iron must be equal. All right? Based on all of these hints, I think you should be able to do this problem here. Okay? So I'm going to stop here. On Wednesday, we're going to start a new topic, entropy. And on Thursday, you have your second test. And on Tuesday, I have a review session at 7 o'clock. And just to remind you, Frida is having a review session tonight at 8 o'clock. All right, I'll see you guys later.
Will you still have regular office hours?
Not on Tuesday.
Is it the review sessions in here?
Yeah, the review session is here. So the review session is at the same time as my office hours.
And then Wednesday?
Wednesday I will have regular office hours.
This times this to get this. No. Yeah, that's what I did. And then I put this.